California did not have one earthquake swarm in 2026. It had three, spread across 400 miles, and none of them is the story you think it is. In January, a swarm near Indio triggered over 250 aftershocks. In February, 33 quakes shook the Bay Area in 90 minutes. In May, more than 350 tremors rattled the Salton Sea. Officials called each one ordinary, but a new stress reconstruction released in June found something the swarms never touched, a single mountain pass that may decide whether California's next major earthquake stays contained or becomes something larger. Start with the first one, January 20th, just after sunrise in the desert. A magnitude 4.9 earthquake struck 19 kilometers northeast of Indio, deep in the Coachella Valley. The United States Geological Survey confirmed it within minutes. Then the aftershocks began. Not a handful, over 250 of them, 11 strong enough to be felt on their own, rolling through Thousand Palms, Indian Wells, 29 Palms, and Palm Springs. Residents described windows rattling and shelves shifting. Nobody was hurt. No structures collapsed. By every technical measure, this was a normal California earthquake sequence, the kind the region produces several times a decade. USGS scientists ran the numbers the way they always do after a moderate quake like this. Their forecast gave a 5% chance the initial shock was actually a foreshock, meaning something larger could follow within the week. But the deeper numbers told a calmer story, a 0.4% chance of a magnitude 6 or higher, and a vanishingly small 0.04% chance of a 7. Low. Not zero. Low. That distinction matters because in earthquake science, low is not the same as safe, and it is not the same as guaranteed either. For now, this looked like the San Andreas doing what it has always done, shake, settle, and wait. But looked like is doing a lot of work in that sentence. For a fault system that produces small earthquakes constantly, the real question was never whether Indio shook, it was whether Indio was really finished, except it did not stop there. 13 days later, 600 miles north, the ground near San Ramon started moving in a completely different way. Between 6:27 and 8 that morning, 33 separate earthquakes struck the San Ramon Valley in under 90 minutes, ranging from a barely felt magnitude 1.3 up to a sharp 4.2. Items came off shelves in local businesses. Seismologists reassured the public quickly, this kind of swarm does not forecast a bigger quake. But for a region already primed by Indio, the coincidence in timing felt like more than coincidence. Then May. This time it was the Salton Sea, at the fault's southern tip. More than 350 earthquakes in a matter of days, the strongest pair landing at magnitude 4.5 and 4.7. This is the Brawley seismic zone, a stretch of small interlocking faults sitting almost on top of the Salton Buttes. A young volcanic field fed by geothermal heat below the lake bed. 3 swarms, 3 regions, 1 year. It was tempting at that point to assume a single fault was waking up from end to end. That assumption did not survive contact with the map. The San Ramon swarm sits on East Bay fault structure, nowhere near the San Andreas's actual trace. Close on a satellite image. Mechanically unrelated underground. Whatever connected these 3 events, it was not a shared trigger rippling down 800 miles of fault line, which raised a harder question. If the swarms were not talking to each other, why did 2026 keep producing headlines that made it feel like they were? Before testing any explanation, it helps to know what a swarm actually is because it is not the same thing as a main shock followed by aftershocks. In a typical sequence, one large quake releases most of the energy, and smaller ones taper off afterward in a predictable curve. A swarm does not work that way. There is no obvious main shock, and the activity does not necessarily decay the way an aftershock sequence does. Some swarms last a day, some last months. Seismologists studying the Brawley seismic zone have said openly that this makes swarms far harder to forecast than ordinary aftershock sequences, and far easier to misread as something building toward disaster. The easiest answer is the one everyone already believes. Swarms raise the odds of the big one, and that belief is not baseless. After past Salton Sea swarms, USGS forecasters have genuinely pushed the 7-day probability of a magnitude 7 or larger earthquake as high as 1 in 300, sometimes 1 in 3,000. Small numbers in absolute terms, but a real, measurable spike above the everyday background rate. The math behind swarm anxiety is legitimate, but look at what actually happened the last 4 times this exact pattern played out. The 1981 Westmoreland swarm topped out at magnitude 5.8, 8 and stopped. The 2012 Brawley swarm peaked near 5.4 and faded. The 2016 Bombay Beach swarm ran through roughly 100 small quakes and quietly ended. The 2020 Westmoreland sequence, hundreds of tremors deep, produced nothing larger than its own initial main shock. This May's Salton Sea swarm did the same thing all its predecessors did. It decayed. The panic narrative explains why people get scared during a swarm. It does not explain why 2026 feels different to the scientists actually watching the data. That doesn't mean officials treat swarms casually. In past Salton Sea sequences, California's Office of Emergency Services has issued formal earthquake advisories, telling residents across 8 counties that the odds of a bigger quake were temporarily elevated. That's not a contradiction. It's calibration. The 7-day odds genuinely spike during a swarm, then genuinely fall back down when it ends. What the data has never shown across 4 decades of these events is a swarm that reliably escalated into the region's next major earthquake. So the real mystery was never, will this swarm trigger it? It was always something slower, and something the swarms themselves couldn't answer. There is a second candidate worth testing because the Brawley seismic zone sits directly above one of the largest geothermal fields in North America, and a lithium-rich brine deposit beneath the Salton Sea, worth an estimated $500 billion, has drawn new extraction interest. Fluid injection and withdrawal can measurably change pressure on nearby faults. It's a real, documented mechanism, but no monitoring agency has tied this specific swarm to any specific well or project. The mechanism is plausible for the region. It remains unproven for this event. That gap is exactly where a scientific question turns into a viral rumor. That left one place investigators hadn't looked yet, not at the shaking itself, but at the stress sitting quietly underneath it. In June, a study led by geophysicist Liliane Burkhardt at the University of Bern quietly reframed the entire question. Her team reconstructed 1,000 years of stress accumulation across the San Andreas and San Jacinto fault systems in Southern California, using geologic records, not swarm data. What they found, those faults are now carrying the highest modeled stress load in that entire 1,000-year window. In some segments, the stress has already exceeded it. Picture a color-coded map of the ground beneath Southern California, red and orange marking where stress is building toward failure, blue marking where it has recently released. That measurement is called Coulomb stress, a way of tracking how close a section of crust sits to its breaking point. Burkhardt's team built that map by working backward through 1,000 years of earthquake history, reconstructing how much stress accumulated and released along each segment after every major quake. The result wasn't a guess. It was a reconstruction showing, segment by segment, exactly where today's fault system stands compared to a millennium of its own past. Here is why that matters more than any swarm. Northeast of Los Angeles, the San Andreas and San Jacinto faults converge at a narrow geological junction called Cajon Pass. Researchers describe it as an earthquake gate, a point that can either stop a rupture cold or let it jump from one fault onto the other, doubling the length of ground that breaks in a single event. Whether the gate opens or closes depends on one condition, whether the stress on both sides of the pass is roughly matched. Burkhardt's reconstruction found that past major joint ruptures occurred almost exclusively when that exact balance existed on both sides at once. That is the configuration Southern California is now approaching. If the gate opens, the resulting earthquake would not resemble a typical single-fault event. Researchers estimate a joint rupture could reach magnitude 7.4 to 7.8, spreading damage across a far wider area than either fault could produce alone. And it is not an abstract line on a map. The aqueducts that carry water into Los Angeles physically cross the San Andreas near this junction. If the gate opens here, the disruption would not stop at shaking. It could cut off water to a region of millions before repairs even begin. Even Burkhardt's own team is careful about what this model can and cannot claim. A 1,000-year reconstruction depends on how well older ruptures can be dated using trenching, sediment layers, and offset ground features rather than modern seismometers. Earlier centuries carry more uncertainty than the last few decades, and a matched stress condition describes when a joint rupture becomes physically possible, not when it becomes likely on any particular day, month, or year. The gate model identifies a condition. It does not issue a warning with a date attached. That gap between identifying a condition and forecasting an event is where the honest uncertainty in this story actually lives. There is a real-world version of this scenario, and it happened only weeks before Burkhardt's study was published. In late June, twin earthquakes measuring roughly 7.2 and 7.5 struck Venezuela seconds apart, rupturing along a transform fault, the same type of fault as the San Andreas. The rupture began west of Caracas and tore directly toward the city, focusing its energy into a densely populated coastline. More than 3,300 people were killed. Caltech seismologist Lucy Jones pointed to Venezuela's earthquake specifically when discussing California's own risk, describing it as the same type of transform fault rupture directed at a population center that scientists have long modeled for a San Andreas break aimed at Los Angeles. That comparison is not a prediction. It is not a countdown. It is a demonstration in real time of what this particular fault geometry can do when it points at a city instead of open desert. The comparison is real. The forecast is not. That single comparison changed how the whole investigation had to be framed. Up to this point, the story had been about probability, low percentages, modeled scenarios, numbers that stayed comfortably abstract. Venezuela made the abstraction physical. It showed exactly what happens when this kind of fault, moving this way, points directly at the people living near it. It did not answer whether or when California's version of that rupture will happen. It answered what it would look like if it did. And that's precisely the kind of comparison this investigation has to handle carefully, because the instinct is to treat it as a preview. It is not a preview. It is a mechanism borrowed from one part of the planet to explain a risk that exists separately on another. To understand how unusual today's stress level actually is, go back to January 9, 1857. The Fort Tejon earthquake, estimated near magnitude 7.9, tore through more than 200 miles of the southern San Andreas, the last time this segment fully released. That measurement comes with an asterisk. In 1857, there were no seismometers. The magnitude is a reconstruction, built from the extent of ground rupture, contemporary written accounts, and comparisons to similarly sized transform fault earthquakes elsewhere. It's a strong estimate. It is still an estimate, not an instrumental reading. That was 169 years ago. Since then, the fault has been quietly reloading, segment by segment, for nearly the entire span Burkhardt's study measured. But history also hands us a caution against reading too much into any single alarming signal. Between November 1976 and November 1977, a swarm struck the San Andreas near Palmdale, the first documented swarm on that segment since instrumental recording began in 1932. It followed a genuine measured 35-centimeter uplift of the ground known as the Palmdale Bulge, an anomaly that alarmed seismologists at the time. It did not precede a major earthquake. The fault stayed quiet. That precedent exists precisely to stop this story from becoming a countdown. There is one more transform fault precedent worth knowing, from the other side of the planet. In 2025, Myanmar's Sagaing Fault, another strike-slip transform system, ruptured in a way that surprised the researchers studying it, moving with a complexity satellite data hadn't fully anticipated. The lesson wasn't about magnitude. It was a reminder that strike-slip and transform faults, the same family the San Andreas belongs to, do not always behave the way older models assume. That's not a reason for alarm on its own. It's a reason the Cajon Pass Gate model gets taken seriously instead of dismissed as speculation. So what is actually comparable between Venezuela and California, and what is not? The shared feature is structural, a transform fault rupturing directly toward a major population center, focusing energy rather than dispersing it. What is not comparable is everything else: building codes, fault history, population density, response capacity. California has spent decades preparing specifically for this scenario. A 2008 simulation, still used as the state's reference case, modeled a magnitude 7.8 rupture producing nearly 2 minutes of shaking and estimated hundreds of deaths and billions of dollars in damage. A grim number, but one that assumes none of the mitigation California has actually built. Picture what nearly 2 minutes of shaking actually means. Most earthquakes people have felt last 10, 15, maybe 20 seconds. The shakeout scenario models shaking that keeps going long after instinct says it should have stopped, long enough for already damaged structures to fail on the second or third wave of motion rather than the first. That is the scale the state has been rehearsing against for nearly 2 decades, not because a magnitude 7.8 earthquake is expected on a particular date, but because Burkhardt's research now suggests the underlying stress conditions for something in that range have quietly caught up with the planning assumption. And here is where the investigation has to correct itself one more time. Do this year's 3 swarms actually sit inside Burckhardt high stress zone, the one converging on Kajang Pass? Mostly no. The Indio and Salton Sea activity sits near the stressed southern segments, but not on the specific junction the GATE study identifies. The San Ramon swarm, as already established, isn't on the San Andreas system at all. There is no demonstrated mechanism linking this year's visible shaking to the invisible stress buildup scientists are actually worried about. That is not a disappointing answer, it is the honest one. The swarms and the stress record are 2 separate stories that happen to unfold in the same 12 months. So the unresolved variable heading into whatever comes next is not whether a swarm will strike again. It will somewhere, probably within the year, because that is simply how this fault system behaves. The unresolved variable is whether the slow stress accumulation at Kajang Pass keeps climbing toward, or has already reached, the specific matched condition Burckhardt's reconstruction links to past joint ruptures. That number doesn't update every time the ground shakes in Indio or the Salton Sea. It updates only when researchers get new geodetic measurements of how much the crust on each side of that pass has actually moved. The next real headline in this story almost certainly won't come from a swarm at all. It will come from a satellite pass, a GPS station, or a revised stress map quietly published the way this one was. So separate what is actually known from what is not. Confirmed, the San Andreas and San Jacinto systems are carrying record-level modeled stress, and the Kajang Pass junction has historically controlled whether that stress produces a contained quake or a much larger joint rupture. Interpretation: current conditions resemble the configuration that preceded past large linked earthquakes. Unproven that this specific moment will produce one. Weakness: Burckhardt's model is a reconstruction of the past, not a forecast of the future, and no combination of swarms, stress maps, or historical parallels can currently predict an earthquake's timing. What scientists are actually watching now has nothing to do with the swarms making headlines. It's GPS and geodetic strain data across the pass itself, any migration of seismicity toward that junction, and updated stress modeling as more data accumulates. Jones herself put the honest timeline into a few words. It could be a century away, or it could be tomorrow. What people consistently underestimate, she added, isn't the shaking itself, but the economic and social disruption that follows it, which brings this back to where it started. 3 swarms shook 3 different parts of California this year, and none of them was the real signal. The real signal is quieter than a swarm and harder to put on a map, a slow, decade-spanning accumulation of stress converging on one mountain pass north of San Bernardino, where a gate has not opened in 169 years. Right now, aqueduct pipes still cross that fault trace undisturbed. Seismographs from Indio to San Ramon to the Salton Sea are still quietly logging small, unremarkable tremors. And at Kajang Pass itself, instruments keep recording a stress level that has never been higher in 1,000 years of reconstructed history, waiting like everyone else to see which way the gate goes.